In our studies of the sun, we've talked about observations of the sun, basic physical parameters of the sun, size, mass, brightness. We've talked about the understanding of what's going on in the center of the sun, nuclear fusion, the proton-proton chain, and we've talked about the different interior structures of the sun, such as the fusion core, where actually the nuclear reactions are happening, the radiative region, and then the convective region on the outer part. We've talked about the properties here of the surface of the sun. I don't like the term surface of the sun, but that's what's generally used to describe the photosphere. That's what you see when you look at the sun. The parts that are above that are thin and harder to see. They don't shine as bright as the photosphere. Photosphere is not even really a sharp layer. It's a region. Light shines through it itself because it's a gas. And so we talked about the photosphere and the chromosphere and the corona. Okay. We talked about activity on the sun. We talked about spicules that are going up and down the outer part of the sun, and we talked about the convection that's happening inside the sun, the smaller convection that occurs near the surface of the sun that gives rise to the granules and the supergranules. All of that is basically referring to the stable sun. Then we started introducing the idea of how the magnetic field gets wrapped up, wound up inside the sun, and when it does get wound up inside the sun like that, you have these bundles of intense magnetic field that can arch through the surface of the sun. Gases get caught in that. You get these real pretty prominences, which you see in the background here of this image right here. Okay. Then comes the idea of solar flares. That's when this magnetic field reconnects and releases this unbelievable amount of energy. When that happens, you get this massive, explosive release of energy. And when that happens, then that basically dissociates some of these atoms, molecules rather, into individual atoms. You throw them outwards near the speed of light. They go outwards, they slam into the gas that's already there. And when they do, they slow down when they slam into it. That process also releases a blast of X-rays, something in physics we call Bremsstrahlung radiation, or German for braking radiation. Not braking like this, but braking like you brake a car. Okay, so braking radiation, slowing down radiation. That was an issue that was a big deal in old tube TVs or in any kind of cathode ray tube sort of thing, such as computer monitors, the old tube TV computer monitors. They had so much lead in them to protect the user from the radiation, from the X-rays, that technically it was illegal to throw them away, though that's what most people did, because people didn't know that was actually toxic waste. Well, this blast of radiation is going to be way more than that. It will travel across the entire solar system and then slam into Earth. And so this is actually something that's measurable, that this radiation loading. Now, the radiation does not make it through the atmosphere, so you don't have to worry about that. It stops in the upper atmosphere, but astronauts in space can get this massive dose of radiation. This was one of the big problems they were worried about during the Apollo missions to the moon, and this is a major issue they're concerned about with missions to other worlds like Mars, and that is a major solar flare could create this radiation bath. Well, it actually does something even worse than that. All this stuff slamming up there, in physics we have conservation momentum. So when it slams to a stop, it transfers a lot of momentum into the gas that's there and pushes that on outwards. What happens is, at that point, you get what we call a coronal mass ejection, in which this blast of energy shoving stuff out, slamming into the corona, can actually shove a chunk of the corona outwards across into space. And so remember, the corona is the superheated outermost part of the sun, and now you're taking a big chunk of that and sending it blasting across space as a high-energy plasma bomb. Okay. I'm a huge Star Trek nerd, and so cannot help referencing the plasma weapons used by the Romulans here, similar to this sort of thing. But this blast of high energy plasma going out across the solar system, this we call a coronal mass ejection. It's literally a mass that's part of the corona being spewed outwards. What you see in the slide here is an image of the sun taken by the SOHO spacecraft. It's a European NASA cooperative spacecraft that's studying the sun. The actual sun would be the size of that little circle in the middle right there, and it would overwhelm the camera. So what they did was have a disc sitting in front of the camera, and you can sort of see in the background the shadow of the holder that holds that disc in front of the camera, and so it blocks the photosphere and the chromosphere, but lets the light of what's beyond that shine through. And what you see in here are images of coronal streamers right here, and this is a big blob of stuff detaching from the sun and blowing out across the solar system. Now, if there's a planet in there, remember the solar system is pretty big. If there's a planet in that direction, it's going to slam into that planet at some point. Okay, and so when it does, that affects the planet. Okay, it affects space and environment around the planet. So all of this we call space weather. And so the space weather is tied in part to these coronal mass ejections. The coronal mass ejections give rise to space storms. Okay, this would be like a space hurricane. Okay, and so the coronal mass ejection here, over time, it starts blowing outwards all over there. The coronal mass ejections originate from two different sources. The biggest coronal mass ejections are generally associated with major solar flares. These major solar flares are located in regions of active or convoluted or twisted magnetic fields associated with active regions, sunspot groups. Would be an example of an active region right there. And so near solar maximum, that's where you find most of these coronal mass ejections, near sunspot groups. And now at solar minimum, you would think, well, there's hardly any sunspot groups, so you're not going to get hardly any solar coronal mass ejections. And you don't get nearly as many. You don't normally get as big ones, but you do get a few because there are these coronal streamers near the equator of the sun that can detach and go off as well. And so that it turns out a little bit different process goes on in terms of making that happen. But this is where you get the coronal mass ejections that then give rise to space weather, because when they run into Earth, that's where you get issues, because as they leave the sun, then they are leaving the sun, and then if this big blob of stuff runs into Earth, it starts interacting with Earth's magnetic field. Magnetic fields exert forces on moving charged particles. Plasma is moving charged particles. So the Earth's magnetic field will exert forces on these particles. Newton's third law, though, says for every force, there's an equal and opposite force. So that would suggest to us that these particles coming along, running into the magnetic field of the Earth. As the magnetic field of the Earth makes them kind of deflect and go around the Earth, then what's going to happen is that they're going to exert pressures here on Earth and on Earth's magnetic field. They disrupt the Earth's magnetic field slightly, and when they do, the Earth's changing magnetic field then exerts forces on other things that are of a consequence to us, and so that has effects that we call geomagnetic storms. So this is where we're going to be going next, is actually talking about space weather. Coronal mass ejections are what generally cause the big geomagnetic or space weather storms. You get space weather even without coronal mass ejections. You get solar wind particles, you get other sort of things that are streaming always away from the sun, and they do vary slightly. So there actually is space weather without solar storms, but the solar storms give rise to space weather storms, which are the ones we really are interested in talking about.